At this very moment, two machines are traveling through interstellar space. Not one, two. Most people are familiar with Voyager 1, humanity's most distant creation. The probe that crossed into interstellar space back in 2012 and has continued beaming back data from beyond our solar system's edge ever since. The one carrying the golden record, the one that keeps grabbing headlines, the one everybody talks about. But there's a second spacecraft out there too. Quieter, less famous, less discussed. Traveling through the void 13 billion miles from Earth, heading in an entirely different direction, sampling a completely different slice of interstellar space, and carrying something Voyager 1 lost before it even reached the Heliopause. Something that would turn out to be the single most critical instrument for understanding the edge of our solar system. This spacecraft is Voyager 2. And what it discovered when it crossed into interstellar space, what its unique, one-of-a-kind instrument recorded as it passed through a boundary no model had ever accurately predicted, didn't just confirm what Voyager 1 had found, it contradicted it, it complicated it. It raised questions that Voyager 1, for all its remarkable accomplishments, simply couldn't address. Because Voyager 1 was blind to the single most important factor at the Heliopause, while Voyager 2 was not. And right now, in the summer of 2026, Voyager 2 is on the verge of becoming the most consequential spacecraft in the mission's history. Not because of a new discovery, but because of what NASA is about to attempt with it. A procedure so dangerous, so unprecedented, so completely make or break, that the engineering team has nicknamed it the Big Bang, a coordinated simultaneous overhaul of every remaining power system on the spacecraft, carried out across a communication delay exceeding 16 hours in each direction, with no fallback and no chance for a do-over if something goes wrong. If it succeeds, Voyager 2 buys more time, and everything Voyager 1 is set to attempt in July hinges on whether Voyager 2 survives this first. Stick with me, because this is a story most people have never encountered, and it's more important than anything currently being said about the Voyager mission. Voyager 2 launched on August 20th, 1977, 16 days ahead of Voyager 1. Despite carrying the higher number in its name, this isn't a typo or a clerical error. It reflects the order in which each mission was expected to reach its targets. Voyager 1 followed a faster trajectory, one that would carry it past Jupiter and Saturn before veering out of the solar system entirely. Voyager 2 was assigned a longer, more intricate route, one that would let it accomplish something Voyager 1 never could. Something that, at the time of launch, no spacecraft had ever done before, and nearly 50 years later, no spacecraft has done since. Voyager 2 remains the only spacecraft in human history to have visited all four outer planets: Jupiter, Saturn, Uranus, and Neptune, every gas and ice giant in our solar system, observed up close with instruments built to study their atmospheres, magnetic fields, and moon systems. Voyager 1 visited Jupiter and Saturn, then headed north out of the ecliptic plane, giving up any chance of reaching Uranus and Neptune in exchange for a closer flyby of Saturn's moon Titan and a quicker path toward interstellar space. This was a deliberate trade-off. Two spacecraft, two missions, two different answers to the question of what lies at the outer edges of our solar system. The cost Voyager 2 paid for visiting all four planets was time. Its path, shaped by gravity assists from each planet along the way, took longer to complete. Voyager 1 crossed the Heliopause in August 2012. Voyager 2 didn't reach it until November 5th, 2018, 6 years and 3 months later. 6 years in which Voyager 1 had already been sailing through interstellar space, already measuring plasma and magnetic fields beyond the boundary, already transmitting data that puzzled scientists and forced them to rethink their models. For those 6 years, Voyager 1's readings suggested something extraordinary was happening at the Heliopause. But the picture was incomplete, because the one instrument that could have given Voyager 1 the full story had broken down back in 1980. Here's something about Voyager 1 that almost never comes up when people discuss its Heliopause findings. Voyager 1's plasma science instrument, the device meant to directly measure the temperature, density, and flow speed of plasma, both inside the heliosphere and out in the interstellar medium, stopped working in 1980. Not at the Heliopause, not in interstellar space. It failed before the spacecraft had even reached Jupiter's orbit on its outbound journey. 4 decades before crossing the Heliopause, before any interstellar science took place, the instrument best suited to reveal what the Heliopause truly looks like from within had already died. That meant when Voyager 1 finally crossed the Heliopause in 2012, it had no way to directly measure plasma on either side of the boundary. Scientists could piece together clues from other instruments, the cosmic ray detector, the magnetometer, the plasma wave subsystem. But direct plasma measurement was impossible. They were working around a hole in the data, one that had persisted for 32 years by the time of the crossing, and one they simply couldn't fill. Voyager 2's plasma science instrument, however, was still operational. When Voyager 2 crossed the Heliopause on November 5th, 2018, it carried a functioning plasma sensor. the very kind Voyager 1 had lost before the Cold War even ended. And that instrument, at that boundary, produced a dataset researchers called historic, the first ever direct, simultaneous measurement of plasma on both sides of the Heliopause, inside the Heliosphere and out in interstellar space, captured as the spacecraft made the crossing. 5 papers, published together in Nature Astronomy in November 2019, detailed what Voyager 2's instruments had recorded at the Heliopause. And the findings upended models in ways that genuinely stunned a scientific community that had spent 6 years working with Voyager 1's incomplete picture. The first surprise involved the boundary's thickness. Scientists had expected the Heliopause to be a fairly thin, sharply defined transition, a clean line separating the solar wind from interstellar space. Models placed this boundary as a narrow band, perhaps a few 100,000 kilometers across, where the hot, fast-moving solar wind met the cold, dense interstellar plasma, briefly mingling before separating cleanly. What Voyager 2 actually found was a layer, a distinct transitional zone roughly 100 million miles wide, located just outside the Heliopause. Not on the inside, where solar wind dominates, but on the outside, in territory that was supposed to be pure interstellar space from the very start. Instead, Voyager 2 detected a region where interstellar particles had pushed inward through the Heliopause like roots working through rock, tendrils of interstellar material extending more than 100 million miles inward, blending with the solar environment in ways no model anticipated. Voyager 1 had seen something comparable before its own crossing, though different in character. On its approach, Voyager 1 passed through a region where the outward flowing solar wind had nearly stalled, a stagnant zone just inside the boundary where the wind had essentially run out of momentum before pushing any further. Voyager 2, coming in from a different direction and crossing at a different point, encountered something else entirely on approach, a thin layer roughly the same width as Voyager 1's stagnant zone, but with entirely different plasma properties. 2 spacecraft, 2 crossings, 6 years apart, sampling different parts of the Heliopause, and finding entirely different boundary structures. Stimatios Krimigis, principal investigator for the low-energy charged particle instrument at Johns Hopkins Applied Physics Laboratory, summed up what this meant in a way that captured the scientific community's reaction perfectly. The fact that both probes reached the Heliopause at almost the identical distance from the Sun, 121.6 astronomical units for Voyager 1 and 119 for Voyager 2, was itself deeply puzzling. One crossing occurred near solar maximum when the Sun's activity was elevated. The other happened near solar minimum when activity was low. The size of the Heliosphere was expected to shift substantially with the solar cycle, expanding during high activity periods and shrinking during quieter ones. Instead, both spacecraft found the boundary at essentially the same distance. "We don't understand why that is," Krimigis stated plainly. "We do not understand why." Coming from a senior scientist with decades of Voyager data behind him, that's not a casual remark. It's an admission that something fundamental about how solar activity relates to heliosphere size doesn't match the models. The second major surprise from Voyager 2's crossing concerned temperature. Plasma inside the heliosphere, carried outward by the solar wind, is hot, not in the everyday sense, but in the sense that its particles move at extremely high speeds, which is how plasma physics defines temperature. Scientists anticipated that as this hot plasma reached the Heliopause and met the colder, denser interstellar medium pressing in from outside, the resulting temperature shift would be one of the crossing's defining features. What Voyager 2's plasma instrument actually recorded was different. The temperature drop at the Heliopause was sharp, far sharper than models predicted, with plasma transitioning from the hot solar wind environment to the much colder interstellar medium within a narrower zone than expected. But what stood out even more was what happened to density. Solar wind plasma inside the heliosphere is relatively thin. Outside the Heliopause, interstellar plasma is considerably denser. Both Voyager 1 and Voyager 2 confirmed this, and together their 2 data points gave scientists their first ever stereo measurement of interstellar plasma density. The space between stars isn't empty. It's filled with plasma more than 40 times denser than the solar wind found at the Heliopause. But Voyager 2's plasma measurements revealed something else that reshaped a key part of the picture. The temperature of interstellar plasma, measured directly for the first time thanks to Voyager 2's working instrument, came in at 30,000 to 50,000 degrees Kelvin, scorching by everyday standards, but far cooler than the plasma just inside the Heliopause boundary, which instruments measured at tens of millions of degrees. The boundary was real. The temperature contrast was real. And this direct measurement of interstellar plasma temperature, something Voyager 1 could never provide without a working plasma instrument, gave scientists an actual figure where they'd previously had only theoretical estimates. Those estimates, it turned out, had been off by a factor of 2. The third surprise, one that Ed Stone, the Voyager project scientist at Caltech, who had held that role since before either spacecraft launched, called the most remarkable of all, concerned the Heliopause itself. It leaks, not figuratively, literally. The boundary between the solar wind and interstellar space isn't a solid wall. Particles pass through it in both directions. Voyager 1, on its way in, had spotted what looked like tendrils of interstellar particles pushing inward through the boundary and into the heliosphere. Voyager 2, approaching from the south, observed something different, a trickle of low-energy particles streaming outward from the Heliopause, leaking into interstellar space even before the spacecraft had crossed the boundary itself. This leakage was confirmed at 2 separate entry points, at different times in the solar cycle, in different regions of the Heliopause. Whatever caused it wasn't a localized fluke. It was a fundamental property of the boundary itself, something no model had accounted for before the Voyager crossings. 2 spacecraft, approaching from different directions, 6 years apart, both found the same leaky boundary. Different mechanisms operating on different sides, interstellar particles pushing in on one side, solar particles leaking out on the other, but the same underlying conclusion. The Heliopause is a border that material crosses regularly in both directions. It behaves less like a wall and more like a coastline, with surf running both ways at the meeting point of 2 oceans. The Voyager probes are showing us how our sun interacts with the material that fills most of the space between stars and the Milky Way, Stone said when the 5 Nature Astronomy papers were announced. The phrasing was deliberate and meaningful, not a description of where the sun ends and interstellar space begins, but of how the sun interacts with interstellar space. Not a clean division, but an ongoing, messy, dynamic relationship between 2 environments that refuse to stay neatly separated. Both spacecraft remain, even now, in a disturbed transitional region, not yet in truly undisturbed interstellar space, even at 13 and 16 billion miles from the sun. Both probes are still sampling an environment shaped by the solar system they left behind. Now step back from the science for a moment and consider what Voyager 2 actually represents within the broader Voyager mission, because the discovery itself is only part of the story. When Voyager 2 was assigned its trajectory, the one that carried it past all 4 outer planets before heading into interstellar space, mission planners knew it would arrive later, knew it would cross the Heliopause from a different direction than Voyager 1, and knew the 2 spacecraft would offer contrasting views of the same boundary. None of this was accidental. In the 1970s, working with computing power far weaker than a modern pocket calculator, the Voyager mission's designers built a 2 spacecraft mission specifically to avoid relying on a single data point. 1 spacecraft alone can't tell you whether its findings are typical or exceptional. 2 spacecraft, approaching from different angles at different times, can begin piecing together the full picture. What the planners couldn't have fully foreseen was that the instrument proving most critical to understanding the Heliopause crossing, the plasma science instrument, would fail on 1 spacecraft and survive on the other. That Voyager 2's plasma detector, still functioning after more than 4 decades in the harsh radiation environment of the outer solar system, would supply data Voyager 1 simply couldn't, closing a gap that had existed since 1980. The division of labor between the 2 spacecraft was planned. The specific way it played out was not. That's what Voyager 2 embodies, a planned contribution that ended up exceeding its intended design in ways nobody could have fully predicted. A mission meant to conclude in 1981, still transmitting data in 2026, from a region of space no instrument had ever directly sampled before, using hardware that has outlived every projection made about its operational lifespan. Right now, in the summer of 2026, the Voyager engineering team at JPL is focused on Voyager 2 more intensely than perhaps ever before. Voyager 2 currently has 3 functioning science instruments. Among them is the plasma science instrument that made the Heliopause discoveries possible. The magnetometer still works. So does the plasma wave subsystem. Together, these 3 instruments are delivering something no other tool in the history of astronomy has ever offered: a continuous, real-time, in-situ reading of interstellar medium conditions, taken from a spacecraft physically situated within that medium, moving through it at 34,000 miles per hour. But the power supply is dwindling. The same steady, unstoppable decay affecting Voyager 1's capabilities is happening here too. Plutonium-238 decays at a rate that strips away 4 watts of available power from each spacecraft every year. At launch, each probe carried roughly 470 watts, generated by 3 radioisotope thermoelectric generators. Today, Voyager 2 has slightly more power remaining than Voyager 1, which is why it still runs 3 instruments while Voyager 1 is down to 2 after its cosmic ray subsystem shut down in April 2026. But that margin isn't large, and it keeps shrinking by 4 watts annually. The Big Bang procedure is designed to change that. As described by NASA's Jet Propulsion Laboratory, it involves swapping out an entire cluster of powered components all at once, shutting some down, replacing others with lower power alternatives, to keep the spacecraft warm enough to keep collecting science data. The name reflects its all-at-once nature, not a gradual, one change at a time process tested and confirmed before moving to the next step, but everything happening simultaneously. A total restructuring of how power flows through every active system, carried out in a single coordinated operation over a communication link where each command takes more than 16 hours to arrive, and each response takes just as long to return. The reasoning behind doing it all at once, rather than incrementally, comes down to the danger of intermediate states. During any power reconfiguration, there are transitional moments when the system sits between its old setup and its new one. Those in-between moments can trigger automated fault protection systems, built-in safety mechanisms on both spacecraft that will begin shutting components down on their own if they detect power draw exceeding what the generators can supply. The entire purpose of the Big Bang is to minimize time spent in those risky transitional states by executing every change at once, moving through the danger zone as fast as possible. If it works, if the new power configuration cuts enough waste to reclaim meaningful headroom in the power budget, it could extend the operational life of Voyager 2's instruments by at least a year, possibly longer. And if the Big Bang succeeds on Voyager 2, the same procedure will be attempted on Voyager 1 no sooner than July 2026, with hopes that success there might even allow reactivation of the cosmic ray subsystem that shut down in April. Voyager 2 goes first, not because it matters less, but because it's slightly closer, slightly better powered, and therefore the safer candidate for a procedure that has never been tried before. What's at stake in keeping Voyager 2's instruments alive as long as possible isn't a simple question. It's several layered questions, each pointing to a gap in human knowledge that only these two spacecraft can currently fill. The structure of the Heliosphere is one such question. The 2019 Nature Astronomy papers established that the Heliopause leaks, that it sits at roughly the same distance from the Sun, regardless of solar activity, that interstellar plasma beyond it is denser and colder than expected, and that the boundary's structure varies depending on the direction of approach and the instruments used. But those findings generated as many questions as they resolved. Why does the Heliopause sit at the same distance during both solar maximum and minimum? What actually determines where the boundary lies, if not solar wind strength? What's driving the two-way particle leakage? And how does that leakage change as the Sun travels through different regions of the galaxy's interstellar medium? The overall shape of the heliosphere also remains genuinely unclear. Some models predict a long, comet-like tail trailing behind the Sun as it moves through the galaxy. Others suggest something closer to spherical or even lemon-shaped. Voyager 1 and Voyager 2 are sampling 2 points along the heliosphere's outer edge, one roughly toward the nose, the other toward the flank, and their combined data remains one of the primary tools scientists have for testing these competing theories. The longer both spacecraft stay operational, the more data accumulates, and the better constrained these models become. The interstellar magnetic field represents another open question. Both spacecraft have measured the magnetic field beyond the Heliopause, and its direction carries implications for how the heliosphere is oriented relative to the galaxy's broader magnetic structure. Voyager 2's magnetometer, still active in 2026, continues contributing measurements that help map the local interstellar magnetic field in the heliosphere's southern hemisphere, a region distinct from where Voyager 1 samples in the north. Underlying all these specific scientific questions is a larger concern. What happens once both spacecraft eventually fall silent? There's no replacement mission, no follow-up spacecraft currently in interstellar space, no instrument within 50 billion miles of where these two probes now sit. There won't be one for decades. Once their last instruments go dark, the map they've been building of the interstellar medium stops updating. Every question they raise but never fully answered will remain unresolved until some future mission, not yet funded, not yet designed, not yet approved, eventually retraces their path and reaches the same boundary. Voyager 2's accomplishments, stated plainly, are almost overwhelming in number. It remains the only spacecraft ever to visit Uranus. During its January 1986 flyby, it discovered 10 previously unknown moons and 2 new rings circling the planet. It measured Uranus's extreme 97.77 degree axial tilt and its ice giant interior composition, and detected a magnetic field so misaligned with the planet's rotation axis that it still challenges current models of how planetary magnetic fields form. It's also the only spacecraft ever to visit Neptune. During its August 1989 flyby, the final planetary encounter of the Voyager program, it discovered 6 new moons, including Proteus, a moon large enough that it arguably should have been spotted from Earth long before Voyager arrived. It clocked Neptune's supersonic winds at 2,400 kilometers per hour, the fastest ever measured in the solar system at that point, and captured detailed observations of Neptune's largest moon, Triton, finding active nitrogen geysers blasting material 8 kilometers into its thin atmosphere, and determining that Triton was almost certainly a captured Kuiper Belt object, a world formed elsewhere and pulled into Neptune's orbit by gravity. its surface reshaped over time by tidal heating from a gradually circularizing orbit. Voyager 2 discovered a 14th moon at Jupiter during its 1979 flyby. It gathered data on Saturn's rings, revealing structural complexity previously invisible to telescopes on Earth. It confirmed the active volcanic eruptions on Io first spotted by Voyager 1, capturing Prometheus erupting in a 200-kilometer-high plume of sulfur dioxide frost. And it returned images of Europa's icy surface, the fracture patterns, the scarcity of large craters, the reddish-brown material staining the cracks between ice blocks, findings that first hinted at a possible liquid water ocean beneath the ice. Those images fueled decades of scientific curiosity about Europa as a potential habitat for life, eventually leading to the currently active Europa Clipper mission. All of this came from a spacecraft launched on August 20th, 1977, 49 years ago, built with technology that predates the internet, personal computers, GPS, and cell phones, and originally designed to last only 4 years, still transmitting, still gathering data, still contributing thanks to its unique trajectory and an instrument that survived where Voyager 1's counterpart failed, something no other spacecraft in history has ever offered. Direct measurements from inside interstellar space, approached from a different direction than Voyager 1, using a functioning plasma instrument for the very first time. The Big Bang tests are underway right now. Throughout May and June of 2026, JPL's engineering team has been working through the procedure on Voyager 2, testing whether the simultaneous power reconfiguration can be executed without complications, whether the fault protection systems stay quiet through the transition, and whether the new power setup delivers the efficiency gains the calculations promised. Every command sent during these tests takes over 16 hours to arrive. Every reply takes just as long to come back. Every diagnostic step eats up more than a full day of communication time alone. The team carrying out this work is small. It's always been small. Most of the original Voyager engineers have long since retired, and their successors had to learn programming languages and spacecraft design principles from a bygone era just to communicate with these machines the way they were originally built to be communicated with. The expertise required to keep Voyager 1 and Voyager 2 running in 2026 isn't something found in modern aerospace curricula. It's living institutional knowledge, held by a specific handful of people in a specific building at JPL, knowledge that can't simply be reconstructed from documentation once the last person carrying it retires. And yet they're still there, still working, still sending commands across 13 billion miles of empty space, still waiting 16 hours for answers to return, still weighing the trade-offs between instrument capability and spacecraft survival that define what this mission can deliver week to week. Still, as of summer 2026, keeping 2 spacecraft alive and transmitting from interstellar space, with a procedure nicknamed the Big Bang standing as their best current tool for buying more time. What Voyager 2 found at the Heliopause, what its plasma instrument directly measured, what the 5 Nature Astronomy papers documented, what the leaky boundary, the unexpected density readings, the temperature data, and the magnetic field measurements all add up to, is a portrait of a solar system that isn't sealed off from the galaxy surrounding it. This is what 49 years of continuous operation and 1 surviving plasma instrument made possible. Not a confirmation of expectations, but a string of surprises still being processed, explained, and folded into new models that will eventually be tested by future spacecraft, if and when such missions are ever built, funded, launched, and arrive at their destination. Until then, 2 machines roughly the size of small cars, powered by plutonium sealed into their generators nearly 50 years ago, remain out there in the darkness between the stars, still transmitting, still measuring, still charting a region of the universe no human instrument had ever directly sampled before they got there. Voyager 1 is the one most people know. Voyager 2 is the one that filled in what Voyager 1 couldn't measure. The twin that visited every giant planet, the one that crossed the Heliopause with a working plasma instrument and told us, for the first time in history, what interstellar plasma's temperature and density actually are, measured directly instead of inferred from theory. Voyager 2's signal takes more than 16 hours to reach Earth, arriving faint and stretched thin by the distance, carrying data from a place genuinely unreachable by any other means available to us right now. And right now, in the summer of 2026, NASA is attempting something on this spacecraft that's never been tried before at this distance, a procedure they're calling the Big Bang, a complete, all-at-once reconfiguration, 1 shot, no second chance. And the outcome will decide not just Voyager 2's future, but what becomes possible for Voyager 1 come July. The signal is still crossing 13 billion miles, still traveling through 16 hours of light speed transit, still moving through a communication loop that takes over a day to complete a single round trip. And it's still coming. If you want to know the outcome of the Big Bang tests on Voyager 2 the moment NASA confirms it, if you want to understand what it means for Voyager 1, for the future of the cosmic ray subsystem, for the last real-time data stream from interstellar space that any instrument will provide for at least the next quarter century, Subscribe now and turn on notifications. This channel covers the real science, the verified data, the actual findings from the actual spacecraft, explained with the weight they deserve without inventing anything the instruments never measured. What Voyager 2 found at the Heliopause is genuinely one of the most significant data sets in the history of planetary science, and almost none of it received the attention it deserved when it was published in 2019. We're fixing that, one video at a time. Subscribe, hit the bell. The Big Bang results are coming. The November 18th, one light day milestone for Voyager 1 is coming. The July attempt on Voyager 1 itself is coming. When those results arrive, you'll want to already understand exactly what you're watching. The signal is still